Okay, guys, so let's start. So what we have done so far in this course from the beginning of this semester until last week, what we have done is, given a circuit, how can you analyze the circuit? But the elements we used in the circuit either resistors or voltage sources, either independent or dependent sources. Same thing, current sources, either dependent or independent. These are the components of the circuits we analyzed so far in this semester. Okay. So in this chapter, I started last time to explain what we call op-amp or operational amplifier. Okay. So this is the purpose of this chapter, is to learn if the circuit has an op-amp, how can you analyze the circuit? This is the difference between this chapter and what we did before. So we're going to add a new element. Still, we're going to have resistors. Still, we're going to have sources, voltage or current sources. But we are going to add one more element. This element is op-amp or operational amplifier. So last time, I told you this op-amp, this is the symbol we have to use for the op-amp. It has, this is the output here, and actually it has two inputs. This input here, we call it non-inverting, sorry, this one is because it's negative, we call it inverting input. And we have here, this one is called non-inverting input, okay? Also, it has bias, okay? And the bias, we have to make it something like that. Like, for example, 15 volt, negative 15 volt, or 18 volt and negative 18 volt, okay? So, so actually this op-amp is a chip. That's what I told you, is an integrated circuit or a chip, okay? This chip has eight pins. As I told you, we have two important pins here for the bias, okay? So one is V plus and V negative, this one, okay? So I want you to understand what you mean by bias. I want to make it very clear. Usually, when I use chips or when I use transistors, okay? Transistor cannot work if they don't have a DC voltage. We call it a bias. So if you have a transistor, you have to input here in the transistor, for example, 5 volt and negative 5 volt. So this is not the input. Be careful about what I'm saying here. So this 5 volt, negative 5 volt, they are not the input. They just, you have to use them so that the transistor can work. You got what I'm saying? After that, I can input, this is the input here, small signal. Here I can get a big, if I use it as an amplifier, and get a big signal. So this is the input and this is the output. And this DC voltage, just to make it work, okay? So without this bias, it's not gonna work, okay? It's not the input. So, and most of the chips, something like that. So, most of the chips, they have, you need to input DC voltage, we call it a bias, just to make it working. That is why, although this is one of the symbols we are gonna use, the bias is here, so this is input, output. So here we have two inputs this way, and we have output, and the bias is here, and the bias is here. This is simple, we can use it, but actually most of the time, we just delete this one, because we don't care about it. We don't care. It's already there, so I'm not going to change it. It's not the input, so I don't care about it. But it is there. That's what you should understand. So if I remove the bias, if I delete the bias, it doesn't mean it cannot work without the bias. Very clear statement, okay? You have to input DC voltage to make it work, okay? But because this DC is not relevant to the input or output, so at least when I do analysis here, I'm going to delete them, but it's there, okay? One of the things I told you also last time is you have here, this is the V output, and then you have here V input is, for example, I call it V1 and V2, negative and positive. So the difference here, I'm going to call it V input. The difference between these two inputs, I'm gonna call it V input. So V input here is V1 minus V2, okay, this way. And actually the output should equal again gain times V input. This is like any amplifier. So what is amplifier? What do you mean by amplifier? Very simple. Amplifier is a circuit. This circuit, it has very small signal input and it's gonna amplify it. You can tell from the name, amplifier, okay? So it's gonna amplify. Actually, there are two types of amplifier. If amplifier here, this one is in phase this way, this is we call non-inverting amplifier, or it can be amplified this way. So here, the gain here, for example, you can see 20. That means I'm gonna multiply. Amplifier means I'm gonna get the same signal, but bigger, large. So here 20 times. So here I can say V output should equal 20 V input. Sometimes I get V output, for example, equal negative 20 V input. So negative here is still you do amplification. Still you get it bigger, right? But it is flipped this way. Okay, so this is the meaning of amplifier. So this one is still an amplifier. I have an input and I have an output. Okay, but honestly, usually we don't use it this way. One, because this gain, we call it a gain, this gain is too high. We don't use it this way. Okay. What's the problem if it is too high? As I made it clear last time, you cannot get output voltage greater than the bias. You get what I'm saying? So if, for example, even for any amplifier, okay, so for example, if V output equal gain times V input, okay? And after you did the calculation, multiply V input by the gain, I found it has to be positive 18 and negative 18. So the signal I have to take as the output should be 18 and negative 18. But if the bias is 15, you cannot, so it's gonna be saturated this way. Okay, so it's gonna be, you're not gonna, this part is gonna be this way. Okay, it's gonna be saturated at 15 because you cannot get more than 15. Anyway, so what I'm saying, yes, this one is an amplifier, but I'm not gonna use it this way because this gain is very high. That means for any small signal, it will be saturated. So I'm not gonna use it this way, okay? So the purpose of this chapter, two things. Number one, if the circuit has amplifier, operational amplifier like this one, how we can analyze the circuit? This is number one. Number two, okay, what this amplifier is, how will we use it? How it is useful? Okay, in reality, what practical application? I will talk about this one as well. Yes.
So the positive and negative bias, do those have to be like the same number, just positive and negative, or can they be converted?
They can be different, but usually we make it the same. Depends on what you are going to do with the circuit. Also depends on the data sheet for the op-amp. Sometimes it's for 15, sometimes it is 18. So it depends on what you want to do. Okay. For example, if you want to get a signal. If you want to get a signal here up and down, positive and negative, so usually you make it the same. But I saw sometimes it can be, for example, 0 and 15, something like that. Okay? Yes.
So when it amplifies it and it's in phase, is that inverting or not inverting?
If it is in phase, not inverted because it does not invert. Okay. So if this is the input this way and the output is going to be exactly the same thing, but in phase. This is non-inverted, we don't invert. But if it is this way, we invert because it's like multiplied by -1, you invert it, okay? Anyway, so now, okay, so let's start with that. Again, in this chapter, I will do two things. Number one, if the circuit has an op-amp, how can you analyze the circuit, okay? How can you do that? This is number one. Number two, what are the practical applications for op-amp? Why it's important? That's what I'm going to explain. Okay. So let's start with the first question. How can you analyze the circuit that has op-amp? There are two ways to do it. There are two ways. You can use a model. You can use a non-ideal model, or you can use ideal model. So I will make a model, okay? So what is the model here we have? Let me go to the slides. Yeah, so the model is here. It's like you have here the two inputs here, you have a resistance here, and in the output, you have dependent source and you have a resistance, okay? So so the op-amp will be something like you have here a resistance or input resistance, and at the output here, okay, let me make it bigger, our input, and here at the output you have here resistance or out, and then you have dependent source this way, and here you have V input. The difference between these two is V input. This source, this dependent source is actually A times VI times VI. So all what you have to do, guys, if you want to use this output, we are not going to use it, but let me tell you what you have to do. All what you have to do, if the circuit has op-amp, I'm gonna remove the op-amp, I'm gonna replace it with a resistance here. Also, I'm gonna replace it by a dependent source and resistance as well. So now the circuit became similar to the circuit we learned in this course so far. All the circuit has resistors, okay, and they have dependent sources. So now nothing is new. It will be similar. You can use, now the circuit became familiar, similar to what we did before. Is that okay, guys? So that means what I'm saying is that, for example, just to make it everything clear. So for example, if you have a circuit like this one, and I want to analyze the circuit, you have here a resistance, RF, and then you have here resistance, and then you have V input, and you have ground, this one. If you have a circuit like this one, as I told you, all what I'm gonna do, I'm gonna remove this one, and then I'm gonna put the model, the equivalent model. So now it became line. You have R1, you have V input, and then here you have internal resistance, and this one is connected to the ground. Okay, negative, positive here, and then here I have a resistance R out, and then I have here as a voltage source, a dependent voltage source, and then I have a resistance this one. Okay, so now I'm not gonna work on this one, I'm gonna work on this one, okay? And now the circuit became similar to what we did before, just resistors and sources. That's it, nothing is new, similar to what we did before. Is that okay? Okay. However, we're not gonna do this one most of the time, because what we're gonna do, I'm gonna use the ideal model, okay? So what is the difference? I'm going to tell you what is the difference. That's what you should understand. Number one, ideal model, as I'm going to explain right now, is going to make the calculations are very, very, very easy. This is number one. Okay. However, nothing is for free. So it's going to be easy, but it's going to be less accurate. Okay. So this one is more accurate than this one. But the gain I will get in the accuracy, it does not deserve the complexity I'm gonna make. Okay, so by the end of the chapter, I will give you an example. I will solve the example twice. One time using the non-ideal, and I got the gain 4.999, something like that. And then I solved the same example using the non-ideal model, and I got 5. So that means I make it complex just to make it more accurate by 0.0001. You understand what I'm saying? Okay. So that's why most of the time we're not going to use this one, okay? And we're going to use as an ideal, because the ideal gives accurate results. It's accurate enough. Okay, I don't need to, and it's actually much less complex than this one. Okay. One more thing also I want to tell you guys. This is a model. This is a model. It's not, that means, even if you solve it this way, using this one, practically, it's still this one has an approximation. Yeah, this one is better than what I'm going to do in the ideal model, but even the results you will get here is not exactly the same result as you will get when you do practically, but it should be close enough. You got what I'm saying? Because these chips may change, the behavior may be changed because of the temperature, because of other factors. And also keep in mind, Inside the chip, there is no transistor, there is no resistance here. This is a model, approximation to the behavior of it. Inside it, as you see last time, yeah, this is a circuit inside it, so it has too many transistors or something. So this model is actually its model how it behaves, okay, or how it works. But that's why I want so conclusion. Number one, ideal model is gonna make the calculation much easier, as you will see. Most of the time we will use it. I don't think in exams, in courses, I will ask you to do this one because this one should be accurate enough. This one is more accurate than this one. That's okay, but the error is too small. So, and this one is complex. Also, you should understand, even this model is not gonna be give you exact practically. This one, even this one has an error as well. Okay, but it's very small error. So, but it should be good enough. Okay. Anyway, so now let's focus on the ideal model. So, but before we go to the ideal model, practically, what are these values? What is Ri? What is R0? What is A? So I want to just show you the numbers. Again, this number may change from a chip to another. So when you buy an op-amp, you need to read the data sheet. So here, our input is actually between 10 to the power of 5 to 10 to the power of 12. This is very high resistance, very high, okay? Our out, this one, between 1 ohm to 50 ohm. 1 ohm and 50 ohm is small resistance, small, okay? And the gain actually is 10 to the power of 5. 10 to the power of 5. Is that okay? Okay. And also, the input here has to be very small. The input, the difference between these two, it has to be very small because, as I told you, the output, the gain is too high. The gain is too high, okay? And there is a limit for the output. The output should not exceed the bias, okay? That's why this V input should be very, very small value, V input here, okay? But it's not zero. So here in this model, the input is not zero. The difference between these two is not zero, okay? Anyway, so what we are gonna do, what we will do is, now for the ideal case, the way, as you will see right now, the way we are gonna analyze it, the circuit is, look here, very easy. Look here, guys. Number one, the current here, or the current here, I'm gonna call it I1 or I2. I1 equal I2 equal 0. Practically, it's not 0, but it's very small, okay? Because the resistance here, we have a very high resistance, okay? So anyway, so here, the approximation I will make is actually, I'm gonna assume, instead of having a resistor here that's too big resistance, I will assume it's open circuit. It's like open circuit. This is approximation I did. So number one, very important thing, guys, when I analyze the circuit, number one, any current entering here is 0, okay? And even if you come here, you can see this is the input current. It is gonna go to the base of the transistor. Usually the base current is very small current. So if you learn about transistors, the base current is usually a very small current. Anyway, so but we can assume the current is 0 as an approximation. This is number one. But that doesn't mean the output current here is 0. I didn't say the output current is 0. I didn't say that. So the first thing I'm gonna do when I analyze the circuit, number one, no current is gonna enter here. This is number one. Okay. Number two, here I'm gonna say V1 equal V2, or VI, which is V1 minus V2 equal to 0. This is also approximation, because in reality, there is very small voltage here. Because if the input is really 0, 0, the output has to be 0, because don't be confused. Okay, the output equal AVI. So you are telling us Vi is 0, that means V out should be 0. Okay, no, what I see, V input is not 0, it's a very small number, but because it's a very small number, I will make approximation, I will say V input is 0. Look at what I'm saying? V input is the difference between V1 or V2. That's it, that's it. So I will show you right now, if you have a circuit how, so I'm gonna say it again, it's you have here two factors, a very important factors, or two approximation I will make. Input current here, 0. Input current here, 0. This is number one. Okay. Number two, V1 equal to V2. These two voltages are equal. You got what I'm saying? You will see right now when I do analysis, it's very, if you understand what I'm doing here, it's going to be very trivial. For example, I will give you very simple example to understand. These are the two things I'm going to use. Okay. For example, if you have here resistance this way, I have here V1, I have here, and then I have a resistance this way to the V out this way. Okay, look here, guys. I can say there is a current here, okay, and here there is no current here, no current is going to enter. Let me use a different color. Okay, so I have a current here, but nothing will enter here because we agree nothing is going to enter here. Okay, and this current, all this current is going to go this way. So the current, if you apply Kirchhoff current law here, so this current enter here should equal to this current. Nothing is coming here. Okay, this is number one. Number two, because I know this is V, this is 0 volt, so this one also should be 0 volt. Because V1 should equal V2. So if I know one of them, the second one should equal. That's it. So using these two factors, you will see right now how it will be very trivial, very easy to analyze circuits that has op-amp. Any questions? Okay. Let's start with this example here, guys. In this example, as you see here, by the way, you can observe here, we always make a feedback. So the way usually, the way you use it in most of the applications, usually I make a feedback from the output to the negative input here, or V1. Usually we use this one, okay? Anyway, so let's see if you have a circuit, something like that here, okay? So, and I want to calculate the voltage here. What is the voltage here? Okay. So how we can do it? Okay. Let's see how we can do it. So here, look at this circuit here, guys. What is the current here? This is a current source. So what is the current here? 20 microampere. This current should be divided. Some current will come here and some current will come here. But because we know this current is zero, so all this current has to come this way. Make sense? But don't forget there is a current here, so I can't say, this is a very important thing, don't make these mistakes. This current is going to be the same current here because nothing will come here. But I can't say, very important thing, I can't say this current equal to this current. Please don't do that. So this current here, all this current is going to come this way because nothing will enter here. Okay, so this current will come here, come here, come here. So this current is the same like this current here? No, I didn't say that because there is output current here. I can't ignore it. And you got what I'm saying? And sometimes I don't need to calculate it, okay? So, but you should understand the current here does not equal to the current. So the first thing here you can know is, I want to calculate V4 here, okay? So if you apply Kirchhoff, current law here, I can say this current equal to 0 plus this current, okay? That's what I did here. I did here this current here, this current which is V1 minus V4, Ohm's law, V1 minus V4 divided by 40, as you see here, plus 0, which is this one here, should equal to 20 microampere. As you see. Make sense? Is that easy? Okay. So I need to get V4 because that's what I'm asking you to do in this question. I want you to give me V4. Okay. So now I have this equation. I have this equation here because of current Kirchhoff current law. I need to find V4. Okay. So all what I need to get V1. If I can get V1, okay, I'm done. So V1 should equal V2. Two things as I told you. Number one, input current equal to 0, V1 equal to V2. V1 here is equal to V2. That means if I can get V2, okay, I am done because V2 is equal to V1. Okay, let's see how can we get V2 here. How we can get V2. So what I can do here, I can also apply Kirchhoff current law. We have a current, this current here, plus should equal this current here, which is V3 minus V2 divided by 30. Yeah, that's what I did here. This is the current input. So the input current here is V3, as you see, V3 minus V2 divided by the 30 should equal to 0, output current 0 plus 60. 0 plus 60. Is that okay? And here, this is 0. So what is V3? This is 0. So what is V3? Should be negative 2.75. Is that confusing to some students? I did it many times. So here, if you have a voltage source this way, this is positive and negative, and this one is 3 volts. What it means? It means A is greater than B by 3 volts. So VA greater than VB by 3 volts. So if this one is ground, so if this one is 0, okay, so this one has to be 3. Okay, if this one is 2 volts, so this one has to be 5 volts. So that the difference between them equal to 3. Okay, so what happens here, I give you in this question, I give you this one, I think 2.7 something, but this one was ground. This one was 0. So because this one has to be greater than this one by 2.6, so this one has to be negative 2.7, something like that. Okay, anyway, so that's what I did because this is 0. So this one should be negative 2.75. Okay, so I know V3. So here in this equation, the only unknown is only V2. Once I get V2 from here, V2 should equal V1. I can easily get V4, which is the output here. Is that okay? I'm going to say again because this is a very serious issue, guys, very important. Again, the current, I can assume the input current is 0, but I can't assume the output current here is 0. You cannot ignore this one. And even in this example, you can do by yourself. This current here is 20 microampere. So this current here is similar to this one, 20 microampere. Okay? You can calculate this current, which is V4. I already calculated V4, which is negative 5.35. Okay? You can divide it by 45 to give you the current here. The difference will give you the current here. The difference. Because if you apply Kirchhoff current law here, you have current here, you have current here, and you have this current. So anyway, we don't ignore this current here, but you ignore the input. You can please don't say, yeah, this current will come this way, and it's going to be the same current here. Now there is some current here, input or output here. Any questions? Yeah, sure.
So where did the 0 come from in that second equation with the ACL for the 2?
Yeah.
From the 0.
This is 0.
Okay.
Yeah, because I'm applying Kirchhoff current law here. We have input current, we have output and output. So 0 plus 60. Okay? 0 plus 60. Okay, let's have more examples. That's what I will do all the time. Two things, very simple. Two things. Input current is equal to 0. Okay, V1 equal to V2. That's it. And then I will apply what we learned before. Kirchhoff current law, Kirchhoff voltage law, Ohm's law. I will apply them here. Okay. Let's see if I have something like this one here. I wanna calculate the voltage here. This voltage here. Okay. Again, I'm gonna call this one V1. I'm gonna call this one V2, V3, and V4. So I wanna find V4 here. Okay. You know the input current here is 0. There is also one thing you know here. Can you know V2? Can anybody tell me what is V2 here? What is the voltage here? Oh, this voltage here should equal to this voltage, right? The two voltages should equal here because this one is 0, the other one should be 0. So I don't need to do anything to calculate V2. V2 almost is given to me. This one, this input here is 0, so this one should be 0 as well. So V2 is equal to 0. That's good. So yeah, V2 is equal to 0. What about V1 here? Can you know V1 here? Yeah, this one is 0 here, and the positive side, this one is 0, so this one should be negative 3.35. Okay, so now I have V1, I have V2. Okay, I want to find V4. Okay, so so let's apply Kirchhoff current law here. Let's apply Kirchhoff current law here at this point. So I have input here, input current, I have output current, and then output current here. Okay, so you can see I know V1, I know V2. If you apply Kirchhoff current here, I will be able to get V3. Okay? If I get V3, it will make it easy to get V4. But let's make it step by step. Okay, so here I'm gonna apply the current here, which is V1. Yeah, so here the current here, which is V1 minus V2 divided by 20 plus 0. Yeah, okay. Sorry, this is input, and this we have two output here. So the input here, V1 minus V2 divided by 20, as you see here, this is the input current. The output current should be 0 because of this one, plus V2 minus V3. So you can see in this equation, we have only one unknown in this equation, which is V3. Because I already know V1, I already know V2, because V2 is equal to 0. So if I do that, I will be able to calculate V3 here. Is that okay? Okay, again, I want to get V4. Yeah. So what you can do here, because you know V2, V3, and this one you don't know, if I apply Kirchhoff current law here, I will have an equation that has only one known, which is V4. This way. So the input current here, input current, V2 minus V3 divided by 40. Yeah, V2 minus V3 divided by 40. What I'm doing right now, I am applying Kirchhoff current law here, okay? And then the current here is V3 divided by 10. V3 minus 0 divided by 10, which is here. Plus V3 minus V4 divided by 8. Okay? So now this equation has only one unknown, which is V4. Okay, once I get V4, I'm done. Very easy, very trivial. Okay? As long as you apply it as I'm teaching it, as you are applying it correctly. Okay? So here, this current will come here, and there is some current here. So you can calculate this current if you want, because once you have V4, you know this. Once you have V4 and V3, you can calculate the current here, which is V4 minus 0 divided by 20, and then you can get the current here, V3 minus V4 divided by 8. Okay, and then you can apply Kirchhoff current law here. You have this current, you have this current, you can get this current here. Any questions? Is that easy? Yes.
Is there any output from the outlet? Anything coming out of the outlet?
Before, what do you mean by output?
If the input on the left side, is there any right side or on the outlet? Right.
No, then I want to calculate the voltage here. You got what I'm saying? The voltage here, V4. I don't know what you mean by output. So this circuit has one input here, this circuit, and we have one output here, okay? Here, I'm just using this one as an example. How can you do an analysis? But I will give you circuits that are doing something like amplification, okay, like a difference amplifier, okay. But anyway, here I'm gonna get the output from you. I don't know, I don't understand what's your question. So the output of the circuit is here, the input is here. Okay. Let's have one more example here. Example number 3 here. Again, it's the same thing. Two things. I'm using two things. Number one, input current equal to, say 0. Repeat after me. Input current equal to 0. That's number one. Okay, for the two inputs. Number two, V1 equal to V2. So if I know one voltage, I know V1, I can get V2. If you know V2, can get V1. Very easy. So let's do it here. Here I'm asking you, you have to find the currents in all resistors. So I want to find all the currents in all resistors. So I want to find this current here, or I want to find the current here, I want to find the current here, okay? The thing you should not apply here, you know, the output should equal AV input. So here you should not apply, you should not use this one. The output, you should not use this one here. Why you should not use it? Because I'm assuming V input is 0. So this is not going to help you here in case of ideal, in case of the ideal. Okay, so I'm assuming the input is 0, although it is not 0, but it's very small enough to say it's 0. So here the input, I'm going to assume it's 0. So please don't apply this one. It's not going to help us at all here in this case. Anyway, so let's start. How can you get the current here? How can you get this current? Okay. I want to find all currents here. Okay, let's start. Okay, so I know input current here is 0. Input current is 0. I know input current is 0. Also, I know this voltage here equal to the voltage here. Make sense? It's the same voltage. Okay. So that means, what is the voltage here? 1.2, right? Because this is a ground. This one is ground, so this one 1.2. Because this one is 1.2, this one should be 1.2. So usually this questions, you have two inputs, V1 and V2. Usually I give you the voltage of one input, and then you have to say the other input should equal to this input. Okay? And that's what I'm doing here. So here this input is 1.2, so this one should also 1.2. So anyway, so I already know the voltage in the middle. Okay? And I know there is no current moving this way. I know that. So yeah, so the first thing I'm gonna say here, I'm gonna say V2 is equal to V1, V2 is equal to V1 equal 1.2. This is number one. Okay. Number two, if you apply Kirchhoff current law here, so we have input current here, we have output current 0 plus this one. Okay. So if you apply this one here, it should be V output minus V2, as you see here, V output, yeah, here, V output minus V2 divided by 12, okay, should equal to 0 plus V2 minus 0 divided by 2, as you see here. The good thing is this equation has only one unknown, which is V output. This is the only unknown we have, because I already know V2, okay? Because of that, I can calculate V output. I found here the V output is -6. Now, I have all the voltages, actually. So I know V1, I know V2, I know V out. So I can calculate all currents, okay? So the current here should equal the same current here because nothing is coming here, okay? So I can say the current here is actually V output minus V2. I already know V2, right? Divided by 12, it gives you current here, which is the same current you have here. If I want to calculate the current here, it should be V output, which is -6, minus 0, divided by this current, which is 10. So again, what I found here, I found this current, I1, I10, this current here, I found it is -0.6, negative. Because this one negative, that means the actual direction of this current is this way. This is the actual direction, okay? The second part of the question, which is also very interesting part, I want to find, we agree from this course, and we did it before, the amount of power generated should equal to the amount of power consumed. Is that right? Who is generating power here? This source is generating power. Who's consuming power? The resistors here. Okay. So now I'm asking you, you have to find the power generated and the power consumed. Very easy. You know how you can do it. I times V. I times V. Okay. There is something interesting here. Okay. So let's. So I will do it here. Let's start with this source. How much is the current I have here? 0. So the power consumed, and this is the interesting part, very interesting part. So I have a source, okay, and the current consumed from this source is 0. Yeah, 0. Okay? Actually, it's not 0, but it's very, very small, very close to 0. Okay? So that means the power consumed here is equal to 0. Sorry, the power generated here is equal to 0. Nothing. I'm not going to take any power from this source. It's going to be 0. Okay. So the power here generated is equal to 0. Now, let's look at the power consumed here. Okay, you know the power consumed should be I times V, voltage drop, or it can be I square R, I square R. So I have R, I have I, so I can calculate. So I calculated for the 3 resistors I have. I found total we're going to consume power by 8.64. This is the power consumed by the 3 resistors I have, I square R. So power consumed 8.64, the power generated from this source is 0. What's wrong here? What's wrong? The problem now, please, what's going on here? The power generated does not equal the power consumed. The total power generated is 0. The total power consumed is 8.64. How is that? Okay, okay, let me let me see the question in a different way. How can we consume power here if this source is not producing power? If we don't consume any power from this source, where this power is gonna come from? Yes, it's from the op-amp, but how? From the bias. You got what I'm saying? Because simply this is not the everything here. We have a bias here. We ignored it just for the calculation, but you should understand there is power, there is current consumed from the bias here. You understand what I did here, guys? Again, what I did here is I consumed it. We have source, we have resistors. I found based on the calculation, the power consumed by all resistors is equal to 8.64. I found the power consumed from the source. This is very interesting. The power consumed from this source is almost 0. Okay, so this source, I'm not going to take any power from this source. Okay, 0, because I'm not going to take, there is no current drawn from this source. Okay, so that means the power generated does not equal the power consumed. Okay, you have to tell me, wait a second, there is something missing, you did not calculate. Here, there should be another source, another 2 sources here. I just removed them because to make it easy. But there is another source, it's not here. The source is, we have a bias. The bias is a DC voltage. This DC voltage should be consumed. So this amount of power is not gonna come from this source. It will come from the DC voltage. DC voltage or the bias, okay? That's what I'm explaining here. Any questions? Okay, starting from now, I will start. I almost finished how we can analyze the circuit that has op-amp. Okay, starting from now, still I will do analysis again here, but I will do it on a practical or real practical circuits. Okay, because I told you the purpose of this chapter is to learn 2 things. Number 1, if you have a circuit that has an op-amp, how can you analyze the circuit? And that's what I did. Okay. The second part is how we can use the op-amp, what application, why it's used. That's what I'm going to start explaining here. Okay. This is the first circuit you should know for the op-amp. This is actually here. I'm going to use. Okay. This circuit here is actually how can you use the op-amp as inverting amplifier. Inverting amplifier. Okay, so actually, let me put it this way. Look here, guys. I told you actually what happens here. If I want to do amplifier, so when we to do it, I can put the input here, the input, and then I take the output from here. Okay, and the output should equal A the input. But actually, usually we don't do this way. Why? Why you don't do this way? Because the gain is too high. Okay, for any small input, you will reach the saturation. Okay, and also I have no control in the gain. So this gain, for example, if it is 10 to the power of 15, okay, I have no control. I can't control it. Okay, I can't make it 10, 20. So actually, that's why I'm not gonna do amplification this way. The way I'm gonna do amplification is, and the first circuit you need to memorize the circuit. I'm gonna tell you one. But the first circuit you should. This is the first use The first way we can use op-amp. I can use op-amp to do inverting amplifier. Inverting amplifier. In case of inverting amplifier, this is the negative and positive this way, and then I have to connect the resistor. I have to make a feedback this way from the V output and the negative part. Always make a feedback from the output to the negative part. Okay, and then I'm gonna connect the negative to the ground, and then I make resistance here. I put the input. Okay, so if you make this connection, this is a very well-known connection. This one I can use it as an amplifier. Okay, actually the relation V output divided by V input equals the gain of the amplification, and in this case should be equal negative RF divided by R1. That means V output should equal negative RF divided by R1 times V input. You got what I'm saying? So that means if I can select this ratio, if I can select the resistance, so that this ratio becomes 10. So I'm gonna multiply by 10. And what this negative means, the negative is gonna flip it. Okay? So if you have a signal, for example, if you select RF divided by R1 equal to 10, that means you multiply, I'm gonna multiply the input by 10. But because of this negative, it's gonna be flipped. Okay, so if you have a signal this way, I'm gonna have a signal that is multiplied by 10. So if you can come here until 1 volt, for example, negative 1. So the signal I will get is gonna be multiplied by 10. So it's gonna become exactly same signal, but here should be negative 10, here should be positive 10. As long as you don't, again, as long as you are far from the bias, I can't get voltage greater than the bias. Okay. Okay. So now I amplified the input. This is the V output I'm gonna get. This is the V input, and this negative, the negative I have here because you flip it this way. Okay. Or that's what inverting. That's why this one is inverting amplifier. Any questions? What I will do, you need to memorize this circuit, very important circuit, okay? What I will do right now, I will do analysis again, just like a practice. I'm gonna do analysis to prove to you why V output should equal minus RF divided by R1. Why? How you got this one? It's like a proof. But what you need to learn now, the first way I can use op-amp. The first way I can use the op-amp as inverting amplifier. Okay, and the way you have to do it is positive connected to the ground, negative has to connect it to RF, okay, and this is V output, and then here we have R1, and we have here V input, okay, and as I told you, V output should equal negative RF divided by R1 times V input. So this is inverting amplifier, and I can control it. I can control the amount of gain by just changing the values of resistors. I can control the amount of gain. Okay. Now let's do the analysis similar to what we did before. Let's do the analysis to prove this one. Okay. You need to memorize this circuit. Okay. It's very easy. But anyway, so let's see. This one is ground, 0 volt. So what is the voltage here? 0 volt, right? The ratio has to be equal. So this one also 0 volt. Okay. So now the proof is very easy. So here I have I1, here I have I2, and I have 0 here. So if I apply Kirchhoff current law here, if I apply Kirchhoff current law here, so I1 should equal to 0 plus I2. Makes sense? Okay. What is I1? I1 is actually V input minus 0 divided by R1. Okay. What's I2? I2 actually is 0 minus V out divided by RF. That's it. I'm done. So anyway, so here, if you just do the math, so you will find V output should equal negative RF divided by R1 times V input. You need to memorize the circuit. You need to memorize this formula as well. This is how can we use this way, how I can use it as inverting amplifier, and I can control the amount of amplification by selecting the resistors RF and R1. Any questions? Any questions? Okay. Now, the second circuit you need to know is non-inverting amplifier. Non-inverting amplifier. Okay. How I'm making it very easy. How it will be different from what you did here? Very small change. Look the change I will make. Okay. Oops. Let me remove. Look the change I'm gonna make. I will make very small change. Because of this small change is I'm gonna make it instead of inverting, it's gonna become non-inverting. You know the change I will make? All what I'm gonna do, this is V input, I'm gonna put it, I'm gonna replace it with the ground, and the ground will come to here. That's it. So again, if V input is connected to negative, it's inverted. But when I put V input here to the positive side, and then this ground to come, if I switch them, it becomes non-inverting amplifier. Let me finish, okay? So let's do it and show me how it works. I will do analysis again. So I just wanna tell you if you memorize one circuit, it's easy to memorize the second one, okay? So here the circuit is the inverting. You remember the inverting, okay? The inverting is you have here RF, the output RF, and here ground, here resistance, and V input. Okay, R1. If I want to make it non-inverting, very easy, small change. So here, you have here ground, you have positive, you have here V output. I'm going to connect the resistor RF this way, and then I'm going to put V input here, resistance, then ground. All what I did, I just switched these two. Okay, if you do this way, actually the relation now becomes V output equal to 1 plus RF divided by R1 times V input. Here, the relation was V output equal negative RF divided by R1 V input. This one is inverting, so if you have input this way, the output will be this way. But this one is non-inverting. If you have input this way, the outputs will be in phase this way, but amplified by this amount of gain. So the gain here, RF divided by R1, but the gain here has to be 1 plus RF divided by R1 in this circuit. Okay? Okay, now I will do analysis again. I will do analysis to prove how you come up with this formula. Okay? So let's do it. I'm gonna do analysis now before I take questions. Okay? So again, it's the same thing. We know that V1 equal to V2, or sometimes you call it V plus equal to V minus. That means this input equal to this input. This one is V input. So this one should be also V input. It's the same. Okay? And then same thing, I will apply here Kirchhoff. I'm gonna assume this is I1. We have 0 here, and then we have I2 here. So here I1 equal to 0 plus I2. I1 actually is 0 minus VI divided by R1. I2 actually is I2, which here is actually V input minus V output divided by RF. Okay. So now, if you just do mathematical, if you just mathematical manipulation, so this one should be minus RF divided by R1. Okay, VI equal VI minus V out. Okay, so here I'm going to bring V out to this side. So V out should equal V input plus RF divided by R1 V input, which is the same formula. Okay, guys. I proved it. So conclusion, before I take any question, I'm gonna summarize what I said. What I said very simple. if I connect, I'm still right there? You need to be with you. So conclusion, I can use op-amp like inverting amplifier. And already you know what I mean by inverting, and what you mean by amplification. Amplifier means I'm going to get bigger, signal bigger, okay? Or you can use it like non-inverting amplifier. The two circuits are very close. I just changed the location of, so here, if you have here, almost the feedback we make almost to this input here, the negative input, almost. RF, here the output, okay, and then you have here R1, and then here we have the input, and then we have the resistor here. And this way, the output should equal negative RF divided by R1 times the input. And then by selecting the values of the resistor, I can control the gain. I can make different gains. The second one, non-inverting, all what I'm going to do here, negative and positive, okay, the output, and then this one here, I'm going to say the input is here and the ground is here. Okay. And in this case, the output should equal the input times 1 plus RF divided by R1. Okay. One thing I can see here, if you make this ratio RF divided by R1, so RF divided by R1 can be less than 1. If you want, yes, you can do that. But here, the gain has to be greater than 1. Okay, always the gain here has to be greater because it's 1 plus something. Okay. Before I take questions, the one thing I want to explain is this circuit here is similar to what you have in the book. In the slides. The same circuit, but what I did, I flipped it. So everything is the same, but I flipped it. So when I made the negative here, I guess. So I made it this way, okay. And the input was here, positive here. That's it. But I just flipped it, but it's the same thing. Okay, it's the same circuit. I will show it right now. But this is similar to what you have on the slides, but I just flipped it. But it's the same. You have questions? Thanks. Any other questions here? Okay. So now, this is for A. Yeah. Look here. It's the same thing. I just flipped it. So the negative is here. R1 is connected to ground. R2, which is RF, and the input comes from here, and this is what I accept. Any questions? So now you know now how can we use the op-amp to make inverting amplifier, and how can we use it to make non-inverting amplifier. You know that in each case, you know the formula. V output equal gain V input. And the value of the gain, you can control it by changing the ratio of the resistors. So by changing the values of the resistor, you can make the gain 5, 10, 20, whatever gain you want, you can make it. But keep in mind, the output cannot be greater than the bias. Otherwise, it will be saturated. Yes.
Since when you flip the positive and negative, it doesn't matter. Since the
It doesn't matter. It's like it doesn't matter. It's exactly the same thing. Okay, it's like if you have a circuit and then you rotate it this way and this way, the connection is the same. Okay, I'm not the one who made it this way, but that's okay. It's the same thing. Okay. Any questions? Yes.
In this class, are we usually going to ignore the bias, or are we going to have to work with that as a limit? Because in the other question, it was like a power source.
This class I'm not gonna you should understand the output voltage cannot be greater than the bias. Practically speaking, what I'm saying, you should understand if you have, for example, if you have gain of 10, for example, if the gain is 10 and you have a certain bias, so that means this will make a limitation on the input. The input should have a certain value, otherwise, because of the bias, will be saturated. You understand what I'm saying? But I'm not going to ask about that. Okay, I won't ask about that. But I want you to learn it. If you want to do it practically, and for some reason, if you do it and you find it saturated, you should know two things now. You should know there is a limit on how much input you can input it, because you cannot exceed the bias. Number two, if you do it practically, and then if you look at the output, you find the output is saturated. So you know what it means. Okay? But again, I'm not gonna worry about the bias. That's why you see all the figures here, I just remove the bias. Okay? Any other questions? Okay. The third way I can use, so now I explain 2 ways how can use the OR. Okay. The third way I can use it, and this is very useful, very important, we use it all the time, something we call it voltage follower. You can take from the English name, voltage follower, you follow, okay? So here, what I will do, this one is actually gonna become the same non-inverting circuit here, this one, but what I will do here is, number one, I will remove this resistor, and then I will make this resistor short circuit. Okay, so I'm gonna take this non-inverting here, and then I will remove this resistor this way, and then I will make this one short circuit. Okay, this is what this is another way to use it. We'll call it voltage follower. Very important, very useful. Okay, I'm gonna tell you how. So here in this case, so now it becomes like here. Negative, positive, then I'm gonna make a feedback this way, no resistor at all, and then V input here, V output here. Okay, so here, what is V output? It's very easy, you don't need to do anything because this one is actually equal to V input, right? So it's actually V output equal to V input, or gain is equal to 1. V output is equal to V input, okay? Okay, so why you call it, you take from the English name, why follower, you follow, who's following whom? Okay, because V output here is equal to V input, so actually I can say the output is following the input. That's why we call it follow. Output is following the input. But man, wait a second. Are you kidding? Are you telling me V output equal to V input? So I can make a short circuit with V output equal to V input. Yeah. For sure, I didn't make it to make the output equal to the input, but it's very useful in other things. Let's explain. It's actually very useful in two cases. Okay. Number one, this is very important. We have a problem. We call it loading problem. Loading. For example, I'm sure 100% you will use this circuit. 100%. Okay. You will use something similar to this one. For example, if you have a microprocessor, you have microcontroller, okay? I'm not sure it's familiar with this terms or not, but microcontroller, you can write a program, it's like a small computer on a chip, okay? You can write a program, I think it's widely used everywhere, mechanical engineering, it's not used everywhere, okay? I'm sure you will use it in chemistry, okay? So anyway, so it's like a small computer, write a program, you can run it to control something, okay? Control a motor, whatever, so you can, it's used everywhere. Okay? Anyway, so if you have a circuit like this one, like a microcontroller, and I want to connect it to, for example, to a motor this way, okay, or I want to connect it to another circuit this way, but there is a problem here. The problem is that the maximum current I can get, for example, I'm gonna just give you some numbers to understand what I'm saying. Okay, so the maximum current I want to connect them this way, so that if the output here you can control the motor using this microprocessor or microprocessor, so you can see it like a circuit number one. Okay, anyway, I want to connect it this way, but there is a problem here. The maximum current I can get from here, for example, 10 milliampere, and this motor, in order for the motor to spin or rotate, it needs, for example, at least 200 milliampere. You understand the problem? So now I have a circuit. I want to connect the output of this circuit to the input of another circuit. That's what I want to do. This is a very practical example. You have microprocessor. I want to connect it to a motor, for example. But we have a problem here. The problem is I can't. This motor needs at least 200 milliampere to spin, but this circuit cannot give you this current. Okay, so what we do here, we connect between them a circuit. This circuit, it has several names. It's sometimes you can call it a buffer. Okay, Sometimes we call it a buffer or voltage follower here. So this circuit, actually what happens here, this circuit is gonna take very little current from this circuit, and then it's gonna give this circuit too much amount of current, okay, like 200 milliampere or whatever. So it's gonna satisfy both sides, the two sides, okay? So I'm gonna take very little, and the voltage here equal to the voltage here. So let me explain what I'm saying. So I think you understand the problem, right? The problem is that I want to connect the output of a circuit to the input of another circuit, but the current, there is a mismatch in the current. I can't get here more than 10 milliampere, but here this one needs 200 milliampere. So I can't connect it directly. I need to put something in the middle. Okay, whatever you have in the middle, sometimes we call it a buffer, sometimes we call it voltage follower, or it's maybe has other names. Okay. So what happens, what this circuit is doing is, this circuit here, V output equal to V input. It's not going to change the voltage. It's like a short circuit, okay? V output equal to V input. But it's going to take very little current from here and can provide too much current here. Make everybody happy. But you need to ask me, where this current is come from? Where this current is going to come from? Bias, yes. So what happens here, this current is actually going to come from the bias here. Okay. So in this case, in a case like this one, I can put voltage follower here. So when I put the voltage follower here, this is a negative. This is a, sorry, it has to be okay. Positive here, negative here. We have a short circuit this way. Okay. Number one. You know the input current here is a very small current, it's close to zero. So I'm not gonna get any current from the microcontroller. Also, you know the input here equal to V output. Okay? But most of the current here will come from the op-amp itself. Okay? This problem is called loading. Okay? There is another problem that can be solved this way. So again, you can see the voltage follower like a circuit. This circuit, V output equal to the V input. Yes, because not amplifier. I don't want to make amplification. I just wanna get here a very small current, and then I wanna get here very large current here. Okay. And I give you another example here. How can you use it? Very useful example. Okay. Remember. Another case, how I can use this circuit. Okay, look here, guys. You remember when I told you any voltage source, in reality, any voltage source should have internal resistance. If this voltage source is ideal, the internal resistance is zero. Okay, so if you have a battery, this battery should have an internal resistance. Okay, so what is the problem if this one has an internal resistance for the battery? So it's not only a voltage source, there should be an internal resistance. The problem is, if you use a battery, if you are expecting this battery is going to give me 20 volt. Actually, it's not going to give you 20 volt. Because when you connect this R, the 20 volt is going to be divided between these two resistors. So the actual voltage you will get is actually, you are expected to get, you have a battery of 20. You connect it to RL. You are expected to get 20. You are expecting the voltage here will be 20. But because there is an internal resistance here, okay, most of the time we ignore it. We assume it's ideal, but actually it's not ideal. We just ignore it because it's usually small. Okay, so what happens here is that if you have a VS source VS base, for example, 20, I'm expecting that there should be 20 here. Actually, it is not. What I'm gonna get here is actually VS voltage division. VS times RL divided by the summation. Okay, so this is the actual voltage I'm gonna get. VS times RL. So there's a ratio here. It depends on how big is this ratio. I can get 90% of the 20 volt. It can be 95%, whatever it is, but there is a ratio here. So I'm not gonna get. So if you have a source, if you have a battery, and this battery should give you 20 volt, you are not gonna get 20 volt because it has internal resistance. Okay. So the interesting thing I can do right now, any source, okay, the interesting thing I can do right now, I can just connect, as you see here, to solve this problem, so that Again, what is the problem? The problem is that the voltage here is not equal to Vs. That's a problem because there is an internal resistance. So how can we solve this problem? Very simple. All what you have to do here, you have to connect voltage follower this way. If I connect the voltage follower this way, number one, current here is zero. Current is zero. Because current is zero, there is no drop, there is no voltage drop here. So this is Vs, this is also Vs. So input is Vs. Okay? There is no drop. So output also is Vs. Okay? So by this way, I can cancel, it's like I was able to cancel the effect. I was able to cancel the bad effect of the internal resistance Rs. So now Vs should equal, the output here should equal to Vs. Let's see if I have, yeah. So yeah, that's what I'm saying here. So you have case one and case two. This case one here, if you don't connect this one, whatever you are gonna get here is not exactly Vs, but it's gonna be a ratio of Vs. But if you connect the voltage follower here, you will get exactly Vs. Okay? So here's a combination or the combined practical source and voltage follower act like ideal voltage source. Ideal means you can, it's like I cancel the impact of the internal resistance. Any questions? Yes.
The voltage follower makes it so the voltage across RL equals the source voltage.
Yes, Vs. Without the voltage follower, I'm not gonna get Vs. I'm gonna get a ratio of Vs. This ratio is because of impact of RSC. Can be 90%, whatever. It's not Vs. Any questions? Yeah, I almost finished. I just wanna finish here. Yeah, I think this is what I explained about loading. How can you prevent loading? Okay, so if you have a circuit here, circuit one, if you want to connect the circuit two this way, the current and you cannot get the same current from here. So actually I'm gonna connect another, I'm gonna put voltage follower this way here to prevent loading. That means input current becomes zero, but the output current here can be big enough because this current is not coming from the input, it's coming from the bias. Okay? So nothing I want to explain here to finish this part, just give me 2 minutes, just one thing here. Okay? So one thing here is I want to show you yeah. So for example, here, if you have this circuit this way, okay, if you have a circuit this way here, okay, and I wanna, what is the output voltage here? The output voltage, it's like you have here, it's like a voltage divider. So here, V input times 60 divided by summation. So as you see here, if I have a circuit, listen to me, just 1 minute, okay? Just I'm finished, just 1 minute. So here again, if you have this circuit this way, the output here should be voltage division, V input times 60 divided by the summation, which is 3 divided by 4 V input, okay? This number one. Number two, if I connect a resistance this way here, because of the effect of the loading, the V output I will get is not the same like this V output. It's not the same, okay? So if you do Kirchhoff current law, whatever, you will find the output voltage here I'm gonna get is actually half the input. So without connecting RL, this is the output I will get. Okay? If you connect RL, you will get different output because of the loading. Because this circuit will make a load on this circuit. Okay? How can you solve this problem? You put here voltage follower here. So if I put voltage follower here, what's going to happen? When I connect these two circuits together, the voltage I will get here will be similar to the same voltage here. Okay, this one. Okay. So this is the same thing. This is what we call loading. So loading means this is the same thing when I told you microprocessor is going to give me only 10 milliampere, but the motor needs 200 milliampere. Okay, it's also the same thing here about loading. So loading, I can explain loading in a different way. I can say I have certain output voltage. Okay, when you connect the other circuit, the voltage will be different. That's exactly what happened here. So I have a circuit here. I have a circuit here. When I connected this circuit or this resistor, I got different voltage. But if I put here voltage follower, I got the same voltage like the original one here. Okay. So now I can say this 30K is not loading, it's not a load, it's not loading this circuit. Here it is loading. So loading, that means you are going to change the output because this resistance will impact, will disrupt the circuit here. That's why the output will be different. Okay. Any questions here? Okay. So next time I will continue. But for now, I explain how can use OM as non-inverting amplifier. Inverting amplifier, voltage follower. You need to know the connection for each one of them. Then you need to know what is the formula. Formula is for the output and the input, and why it's important. Why voltage follower is important? How can you use it? Okay. For short amplifier, you don't need to say why amplifier is important because I have a signal and want to amplify. Okay. That's enough for today. We have the two quizzes who are very distributed. Okay. Sorry. Okay.
Pausa. Pausa.